All right, today we're going to break down one of the most fundamental rules of the universe. I'm talking about a principle that governs literally everything, from a gentle push to a massive rocket launch. So, why is a heavy shopping cart so much harder to push than an empty one? I mean, it seems obvious, right? But what's really going on there? This simple question, believe it or not, gets right to the heart of how things move. And it's not just about shopping carts. This is the exact same principle that explains how your car accelerates, why pulling anything heavy is such hard work, and on a much grander scale, how a rocket even gets off the ground. Understanding this isn't just for physicists. It explains the mechanics of our daily lives and our greatest technological achievements. Okay, let's dive in. So, to get to the bottom of this, we have to take a trip back in time to the man who literally wrote the rules of motion, Isaac Newton. Now, Newton laid out three laws that completely changed how we see the world. But it's the second one that's the real key to our whole shopping cart problem. Okay, so when you read this, the language is pretty old school, right? Motive force impressed. But don't let that throw you. What Newton is describing here is a beautifully simple relationship. He's basically saying that how much something's motion changes is directly related to how much push or pull you give it. It's a perfect cause and effect. And that beautifully complex sentence has been distilled down into this, probably one of the most famous equations in all of physics. Force equals mass times acceleration. F equals ma. So simple, but so incredibly powerful. So the crucial thing here is really understanding what F, M, and A actually mean. Let's break them down one by one. First up, force, the F. This is pretty straightforward. It's the push or the pull on an object. It's that motive force impress Newton was talking about. It's you pushing the cart, it's the rocket engine firing, it's the thing that causes the change. Next, we've got mass, the M. Now, mass isn't just about weight. Think of it more like an object's inherent laziness, or maybe its stubbornness. It's a measure of how much an object resists being moved. The more mass something has, the harder it is to get it going, and, just as important, the harder it is to stop it once it is moving. That resistance, that's inertia. And finally, acceleration, the A. This is the results of the whole process. When you apply a force to a mass, it doesn't just move, it accelerates. It speeds up, or it slows down, or it changes direction. That change in velocity over time, that's acceleration. Okay, so a theory is great, but how can we actually prove it? Well, let's put it to the test. We're going to move to a modern experiment and see if we can watch this law in action. So what we can do is build what's basically a proof machine to test these relationships between force, mass, and acceleration. We're going to use a special low-friction demonstration track, a setup designed specifically to show Newton's second law in all its glory. Let's quickly walk through this setup. First, we've got the low-friction track itself. This is really important because it minimizes friction so we can isolate just the forces we want to study. Then we place a cart on it and attach a pulley system. We'll add some weights to that pulley to create a nice, consistent pulling force. And to measure the acceleration, we'll use these cool little light barriers connected to a timer. So here's that track. It provides a really controlled environment for us. The cart we use has special bearings that let it glide super smoothly, so friction is barely even a factor. And here's how we get our force. A simple string connects the cart, goes over a pulley, and attaches to a weight holder. The force of gravity pulling down on this weight, that is our constant, measurable force. That's the F in our equation. And finally, to measure the A, the acceleration, we've got this digital timer. It's connected to two light barriers, and it will measure the cart's motion with incredible accuracy as it passes through them. Okay, so now that it's all set up, we can run two really key tests. The whole point of this experiment is to isolate each variable. So in test one, we're going to keep the pulling force exactly the same, but we'll add mass to the cart in each trial. The question is, how does adding mass affect its acceleration? Then, for test two, we'll do the opposite. We'll keep the total mass of the system constant, but this time we'll increase the pulling force. So, how does a bigger force affect acceleration? Let's find out. And check this out. The results from the first test show exactly what Newton predicted. The heavier we make the cart, as the total mass goes up, the slower it accelerates. The acceleration goes down. They're inversely proportional. And just like that, there's the answer to our shopping cart question. More mass means it's just harder to get moving. And then test 2 just brilliantly illustrates the other side of the coin. As the accelerating force goes up, as we add more weight to the hanger, the acceleration goes up too. They're directly proportional. It's so elegant. The more force you apply, the faster it accelerates. Simple as that.
Okay, so we've seen the theory and we've seen the proof right here on this little track. But what does this all really mean for the world outside the lab? Why does it matter?
Well, when you look at the data you collect in an experiment like this, you realize these aren't just numbers on a screen. They represent a clear, predictable relationship. They are a physical confirmation of a fundamental rule of our universe. And what's so amazing is that the very same law that moves this little cart, well, it governs the forces needed to accelerate a car, it's used to calculate the immense thrust required for a rocket launch, and of course, it explains why you have to push that full shopping cart so much harder just to get it going. It all comes back to F equals ma. So the big takeaway here is that this law isn't just some formula in a textbook. It's a deep truth about how the universe actually works, and you can see it all around you, every single day. So what other fundamental laws are out there, just governing our world, hiding in plain sight?